Mercury is tiny, close, and strangely remote. From our backyards, it hovers as a faint point of light near the sun, easy to miss and hard to observe. Yet up close, it is a world of extremes. A planet battered by impacts, baked in sunlight, then plunged into bone-deep cold. A planet whose surface tells a story older than Earth's continents. You might expect a nearby world to be simple to visit, but Mercury has a way of turning the straightforward into the fiendishly complex. The reasons reveal as much about motion and gravity as they do about the courage and craft of the engineers who dare to go there. Think of Mercury as a fossilized archive of the inner solar system. Its crust is scarred and ancient, preserved in a state that records the first billion years of planetary history more clearly than most other worlds. The largest scar, the Choleros Basin, is a feature so enormous and violent it reshaped the entire planet. Imagine a crater nearly 1,000 miles across, formed when an object as big as a small continent smashed into Mercury at cosmic speed. The bow wave of that impact traveled through the planet and tore a matching chaos of cliffs and hummock terrain on the opposite side of the globe. Across the floor of Choleros, the ground looks lighter, as if sunlight has bleached it, but it is the mark of rock thrown up and deformed by that cataclysm. Nearby, the Pantheon fossae spread out like the spokes of a wheel, long narrow troughs radiating from a central point. No other known world displays exactly that architecture, and scientists still debate how it formed. Some say a volcanic uplift collapsed to form the rings. Others argue the stresses from a giant impact opened those cracks. Either way, it is a feature that makes Mercury uniquely Mercury. Walk the plains of Mercury in your mind. Vast basins sit next to fields of smaller craters. Every feature named for a creator or thinker. Rembrandt, Shakespeare, Beethoven, each a human peg hammered into an alien geography. The Rembrandt Basin is a wound 440 miles wide. A scar so old its edges softened by later impacts, yet still bearing monuments of false scarps and ridges. These lobate cliffs, the so-called scarps, run for hundreds of miles and tell us something remarkable about the planet as a whole. It has shrunk. As Mercury's interior cooled billions of years ago, the planet contracted, wrinkling its crust like the skin of a dried grape. Those wrinkles are giant cliffs, some rising thousands of feet, evidence of a world that literally tightened its belt as it cooled. At the poles, the contrast grows stranger. There are permanently shadowed hollows inside deep craters where the sun never reaches. Temperatures here can plunge to near absolute zero, and yet radar observations and spacecraft data hint at water ice hiding in those eternal night pockets. Imagine an ice deposit, preserved for possibly billions of years, shielded by the planet's topography from the relentless solar heat outside. On a world that sees the sun as a roaring, giant disk for part of its day, ice seems paradoxical. But Mercury's atmosphere is almost nothing. A thin exosphere of atoms and molecules, so tenuous it behaves like a vacuum for most practical purposes. Without air to spread heat, Mercury becomes a world of extremes, blistering by day, glacial by night. The temperature swing is not an academic detail. It is a brutal engineering problem. At midday on Mercury, rocks can reach temperatures hot enough to melt lead. At night, they cool so far they become brittle. Materials and electronics built to survive on Earth must be rethought for such a place. Thermal control becomes mission control. Insulation, radiators, and carefully timed operations are the difference between success and a burnout husk falling into the solar wind. Reachability is the other deeper problem. It's easy to measure distance in miles, and Mercury's distance from Earth sounds reasonable on paper, tens of millions of miles when close. But rockets are not taxis that go in straight lines. Spacecraft live in a landscape of gravity wells. The sun sits at the center of everything, deep and relentless, and Mercury orbits perilously close to that heart. To get to Mercury, we must fight the sun's pull, and more importantly, we must bleed off orbital energy. When scientists send probes to the outer planets, they accelerate and fling themselves away from the sun, leveraging its gravity. When they aim for Mercury, they do the opposite. They must slow down relative to the sun so the spacecraft can be captured by Mercury's tiny gravity. Slowing down means carrying and burning fuel, and fuel is heavy. More fuel means a bigger launch mass, which means a more powerful rocket, which in turn increases cost and complexity. Shipping fuel to handle Mercury's gravitational problem becomes an exercise in diminishing returns. Engineers solve the problem through clever choreography. Mariner 10, the first probe to visit Mercury, used gravity assists and a carefully planned trajectory to change speed and angle enough to make a handful of flybys back in the 1970s. It gave humanity the first photographs and maps covering about 40% of the surface. Decades later, Messenger took a long, patient route, swinging past Earth, Venus, and Mercury itself multiple times, shedding energy in tiny increments until it could be captured into orbit. It took Messenger more than 6 years to enter Mercury's orbit, a journey that required precise navigation and frugal fuel budgets. Now the joint European-Japanese mission Bepi-Colombo is on its own marathon path, launched in 2018 and still en route, scheduled to arrive after a complex ballet of 9 flybys. Every flyby is a calculation of timing and velocity, a small change repeated until the spacecraft has bled enough speed to be cradled by Mercury rather than consumed by the sun. These orbital gymnastics are expensive and time-consuming, but the science is priceless. Mercury hides clues about how rocky planets assemble and evolve. It has an unexpectedly large iron core that makes the planet denser than one would expect for its size. Why is Mercury so heavy at its center? One hypothesis says a titanic giant impact stripped away a large fraction of the planet's original crust and mantle early in its history, leaving behind a metal-rich core. Another view suggests Mercury formed from metal-rich material nearer to the young sun. Either way, the core is a window into formation processes that shaped all terrestrial worlds, including our own. Even more puzzling is Mercury's magnetic field. Small, slowly rotating bodies usually lack a dynamo in their core strong enough to generate a magnetic field. But Mercury has one, modest though it is. This challenges conventional thinking about how planetary magnetic fields arise and persist. Studying Mercury's magnetism could force scientists to rethink the physics of dynamos and how internal heat, composition, and rotation conspire to create magnetic shields. Messenger taught us another surprising fact. Scientists discovered features called hollows, irregular, shallow depressions in the rock that appear to be relatively young and possibly formed by volatile substances boiling away under solar heating. These hollows look fresh and strange, like scars where material has sublimated and vanished into space. Their presence hints that Mercury might have been far more volatile-rich than previously thought, at least in its crust. That raises questions about where those volatiles came from. Did comets and asteroids deliver them? Or did Mercury acquire them during its formation? At poleward latitudes, we circle back to the paradox of ice. The polar craters, shadowed and cold, may host water ice and organic compounds deposited over eons. Radar from Earth-based observatories registered bright reflections consistent with ice, and MESSENGER confirmed spectroscopic signatures. The possibility that a planet so near the Sun could shelter reservoirs of ice is a thrilling counterexample to easy assumptions about planetary environments. Imagining a human visit to Mercury forces humility and awe. Mercury's day is long. A single Mercury day is 2 Mercury years long because of the planet's 3:2 spin-orbit resonance. The Sun rises and sets in a tempo that makes day-night cycles on Earth feel like a blink. Engineers would need to protect habitats from both scorching and freezing, to manage dust that behaves unlike lunar regolith, and to deal with solar radiation that is far more intense, so close to the Sun. Even robotic explorers must contend with solar pressure that can push and torque a spacecraft in subtle, mission-threatening ways. Despite these challenges, missions continue because the potential returns reshape our understanding of planetary systems. Bepi-Colombo will carry instruments able to probe Mercury's mineralogy, magnetic environment, and interior structure with unprecedented resolution. It carries 2 orbiters, each designed to complement the other, and together they will fill in the maps left incomplete by earlier missions. They will test theories about Mercury's composition, search for the origins of its magnetic field, and characterize the polar ice deposits. Each new data set will force revisions, spark debates, and seed the next generation of questions. Mercury also offers a laboratory for comparative planetology. By comparing Mercury with the Moon, Venus, Earth, and Mars, scientists can test how variables such as size, proximity to the Sun, composition, and internal heat shape planetary evolution. Mercury's unique blend of features, extreme temperatures, a massive core, shrinkage scars, young hollows, and polar ice, creates a natural experiment. Learn Mercury, and you learn about the diversity of worlds beyond our own, including the countless rocky exoplanets now being discovered around other stars. Many of those exoplanets hug their stars in tight orbits. Understanding Mercury helps us interpret those alien systems. If you close your eyes and stand on Mercury's dawn terminator, you would see the Sun hung large and brilliant, an enormous disk lighting the plains like a blinding floodlight. The shadows would be black and long, stretching away into frost-bound darkness. The ground underfoot would creak as it contracts and expands with brutal temperature swings. Above, the sky would be nearly black even midday because there's almost no air to scatter the sunlight into blue. You would feel both tiny and exhilarated, standing on a world that remembers the violent youth of the solar system. Technology will keep pushing the frontier. Concepts once relegated to science fiction are becoming plausible. Solar sail scouts that harness sunlight to brake and maneuver near the Sun. Small glider drones that skim Mercury's surface for minutes at a time. Long-lived landers that use clever thermal control to survive the day-night extremes. Each innovation reduces the cost and increases the scientific yield of exploration. At its core, the story of Mercury is a tale about ambition and balance. It is about the way gravity governs not only planetary orbits, but also our choices as explorers. The planet forces us to design with humility, to accept long journeys and patient planning in exchange for the chance to open a window onto the early solar system. Mercury reminds us that proximity does not necessarily mean access, that the nearest neighbor can be the hardest to embrace. We have mapped only a portion of Mercury's face, and each new image invites more questions than it answers. The scars and folds on its surface are not simply marks of past violence. They are pages in a book we have only just begun to read. In the coming years, as Bepicolombo sends home its first measurements, we will learn more about why Mercury is so dense, how its magnetic heart keeps beating, and whether its shadowed craters hide more water than we dared hope. Until then, Mercury will remain a paradox. Intimate in distance, distant in difficulty, humble in size, and immense in scientific promise. Mercury may seem small and elusive, yet it holds lessons about resilience, mystery, and the power of cosmic forces shaping every world. We hope this journey ignited your curiosity. Stay with us as we venture deeper into the solar system's hidden stories. Subscribe and join us for the next discovery.